to Fred's chart work section of my YouTube videos, which are backed up by the Nav and Radar Section A app. So, chart work. How much do you remember from your RAA exam? I know for me, I did not remember very much. If I'm being perfectly honest, when I'm on watch, if I'm left of the red line, I go right. If I'm right of the red line, I go left. I'm pretty sure, having taught a lot of people Nav and Radar, having taught a lot of people oral prep, that the best will in the world, the last time you did a 3-point fix, in reality, other than checking your position, I'm not saying you don't check your position, but the last time you did a 3-point fix was in your Yacht Master exam. You may have shown deck crew, you may have done this, you may have done that. I could be completely wrong. But I know the last time I got an azimuth mirror out, or I got a Polaris out, was for training. I do verify my position, I do look out the window, I do what I'm meant to do, but I don't necessarily do traditional nav on my Ectus. But you do need to be able to understand it, you do need to be able to keep up with it, and you do need to be able to do it to pass this exam. So I actually quite like teaching the chart work section. The reason is, when I did it as a student, I was terrible. When I did it as a learning teacher, I sat next to a man called Mike, and he will vouch, this is Mike Ferguson, he will vouch how terrible I was at my chart work. I'm not sure who was more scared, the fact that I had to teach people in the future, or that he had an exam. If you do see Mike, do ask him about pencil and how to sign his name. I'm sure he'll love me for that. Anyway, do sign your name on the front of the exam paper, and if it says write in pen, write in pen. Do your chart work in pencil. So let's talk about what you need for your chart work. You need a good 2B pencil. You need a calculator. You need a decent set of parallel rules. Now, for radar plotting, you need the 15-inch radar, parallel rules. And when I started doing all these questions, so I've worked through 10 questions, and I've done them on the charts that you're going to have in your exam. I've done them very similar to exam style questions. I've made them slightly harder, I've made them very similar. They're a good broad spectrum of what you're likely to experience. I actually went out and bought the 18-inch parallel rules because I was struggling to do the lats and longs. And some of the courses to steer are long. So I suggest that you get a set of 18-inch parallel rules and a set of 15-inch. Take them from the group before, just buy them. Look for people who've got them. If you've got a mate who's gone and done their Nav and Radar, if they've watched this video, they've bought the app, they've done everything they're meant to do, they'll pass. Buy their equipment off them. You also need a decent set of dividers. I know a bad workman always blames his tool, but in this case, it does make a difference. You're trying to be accurate. A decent compass, you're going to need that for the radar plotting. You're going to need it for this. These are your tools of the trade, and the rubber just in case you make a mistake. I have a very small pair of dividers as well, just for those very fine measurements, probably a little bit of overkill. What I want to cover in this video is how to do a standard chart work question. Then inside the Nav and Radar app, go to www.fredsapps.com, click on Nav and Radar, and you should be able to download either section A or section B, depending on where you're at with everything, what you want to do before you start your course, if you need any backup during the course, or worst case scenario, you need to resit. you'll have a gut feeling of what you need. Hence why I've tried to split it into two parts. It's a very quick introduction to nav and radar. The syllabus is written down there. You're going to be going through the syllabus in your course. I'm just going to sort of go through it and sort of pick little bits out that make a difference to your ability to do the chart work question. Understand what a magnetic compass is. So that is the magnetic compass on my last boat. I'm sure it's not what you have on your last boat, but it is what the examiner who wrote the exam paper was thinking of, and it's also what they're going to be thinking of in the oral exam. So that is a compass binnacle. The binnacle holds the correctors, it gives it a mount, it has a light in it, it allows you to see this magnetic compass. What is variation? Okay, so variation is the difference between true north and magnetic north. True virgins make dull companions, add whiskey. That's what you learnt for your RAA, I'm sure. Where would you find this variation? Well, if we look at this chart together, you'll see on this chart, this is chart 5048, it is 7 degrees 25 minutes west in 1994, going 8 minutes east every year. Okay. If you want a copy of the notes that I'm working through, you'll find them inside the app. You can download them, read them at the same time as I'm going through it. It's not essential, it's just nice to have a set of notes that match what I'm saying so you can work your way through it. This is designed to be on YouTube just to make sure you're in the right place to move forwards, and then you can make a decision if you want to purchase the app, and or when you're going to see me for the oral, you're in the right place at the right time. Let's talk about this variation. We'll use the variation that's here. So I've got 7 degrees 25 minutes west in 1994, going 8 degrees east every year. What is the variation for the year 2016? Okay, so 1994 to 2016, how many years is that? Use a calculator. 2016 less 1994 is 22 years, times the 8 minutes east times 8 is 176 minutes. Yeah? That's 176 minutes. How many degrees is that? So if you've got 60 minutes in a degree, so that's 2 degrees and something. So less 120, 60 minutes in a degree. So that is 2 degrees, 56 minutes east. So what is the variation we're going to experience? If we were on this chart here, at this time, if we had this, we would have to work out it's 2 degrees, 56 minutes east. This confuses people, doesn't it? This 7 degrees 25 west of north. Yeah, naughty elephant squirt water. It is west of north. So if we're going easterly, it's going to be minus 7 degrees 25 less 2 degrees 56. What does that equal? Now, I can't do that in my head. Some of you who are watching this are going to be like, oh, that's so and so. No, I'm actually numerically dyslexic. When I see that, I see absolutely nothing. I see blank. My brain just can't do it. But what I do know is that an hour and a half is 90 minutes. So don't switch off. Stay listening. An hour and a half is 90 minutes. So one hour or 1 degree, 30 minutes is the same as 90 minutes. Yeah? How did that happen? Well, that is the same as taking across 60. 1 degree is 60 minutes. So 60, 70, 80, 90. So 1 degree 30 is the same as 90 minutes. 60 plus 30 is 90 minutes. So you can express 1 degree 30 minutes as 90 minutes. So using the same logic, 7 degrees 25, if I take that away, that's 6, and that means I bring across 60 minutes. So 7 degrees 25 is the same as 6 degrees 60 plus 25, so that's 8. See, that's numeric dyslexic. I don't even know what I was thinking about. That's probably the next step. My brain works too slow or too fast, one or the other. So that's 5, 6, 7, 8. That's 85. So 60 plus 25 is that. So 6 degrees, 85 minutes is the same as 7 degrees, 25 minutes. The same as an hour and a half is 90 minutes. Now 85 less 56 I can do. Well, I can with the calculator. 85 less 56 equals 29. 6 less 2, I can do that in my head. 4 degrees 29 minutes. West, because I had 7 degrees 25 less 2, it's going easterly, so it's going down. So it's 4 degrees 29 minutes west. Therefore, in my calculations, I would use 4.5 degrees west, 4.5. Happy? You're going to be doing a lot of these, and as we work through the examples together, you're going to have to do this lots. We're going to do it together. You'll be happy with this by the end. You'll probably have forgotten in the future, but it will come back quite quickly. Variation. Remember that true virgins make dull company add west? That's what I learned for my Yachtmaster exam. So variation, if we had a true bearing of 0, 1, 0, and we had a magnetic value of 0, 1, 5, variation would be 5 degrees west. Because we've gone from 0, 1, 0 to 0, 1, 5, therefore the variation must be 5 degrees west. If I was asked to define variation, variation is the angular difference between true and magnetic north, measured east or west of north. That is the answer, that is it. Yep, good. So that's shown in those notes. They're available on the app inside. You can download them, print them, do what you want with them. Understand deviation of the magnetic compass. Understand the reasons for the change in deviation of the magnetic compass with changes in the ship's head. This is covered mostly in section B, and it really doesn't come in so much into your chart work, but you have to understand that deviation is dependent on ship's head. I'm not going to go into magnetism too much. I'm not going to go into permanent magnetism, induced magnetism, because that's theory. But I do need you to understand where this is all coming from. The reference material for this is the Admiralty Manual of Navigation, Volume 1. Yeah, and this is the 1987 version. And as you can see, there's lots of tabs there. That's my source material. This is the Bible. This is what, this is it. This is what your teacher, this is what the person who wrote the exams, this is their book, this is the Bible. It doesn't actually explain why deviation is dependent on ship's head very clearly in the 1986 version. Now, the 1953 version and the 1930s version were fairly clear. If we go back a long way in time, the Admiralty Manual of Navigation 1914, that does explain it. Okay? It's alright, I'm not trying to do a history lesson, I promise. But that diagram there explains why deviation is dependent on ship's head. Now, I could read to you everything that's on that page. I could show it to you, but I don't think it would work very well. So instead, what I have is I have my little boy's boat. Now, I taught some people GSK, and they'd have seen this boat before. This boat is Timmy's boat. Okay, so I'm going to use this just to very, very quickly explain why deviation is dependent on ship's head. Okay? So that's my source material, and this is how I'm going to explain it. Okay? I hope you're all worrying now. What's that? That is a deviation card, isn't it? Or a dollar sign, but it's a deviation card. So when the vessel is pointing due north, you generally have 0 deviation. The reason for that, I explain in the oral prep week. Then, as we go further, we get to 90, we have maximum deviation. Then at 180, we generally have very little deviation. At 270, we have maximum deviation. And again, at 360 or 0, we have very little deviation. Why? Why does deviation depend on ship's head? Well, what I'm going to do is I want you to imagine, so 1 second, I have to get a magnet. These are magnets, okay? These are used for showing lights and things. If I put them together, they'll either attract or repel. That's what magnets do, isn't it? These two seem to be attracting. So, magnets attract or repel. They have a positive charge or a negative charge. If we have a boat, and I draw a boat there, I draw a boat there, I draw a boat there. Now these boats are all the same. They may not look the same, that's distortion of the cameras. Yeah, my artistic skills are second to none. And we're going to say that this way is north, okay? So that way is north. Now, a compass, you hope, points to north. So I'm going to suggest that this is your boat, and this is a compass binnacle, okay? And we'll say that the compass binnacle, we'll make them go that way. The compass binnacle is always going to point to north. Get a Sharpie. Yeah, I'm sorry, my little boy. His name is Charlie, and I'm really sorry because this is his favorite toy. I didn't mean to draw on it. Okay, but it's important that you understand how this works. So we're going to say, okay, there's the boat, that is my compass binnacle. So it's the big brass thing with a magnetic compass in it. And it's going to point to north. So here's the compass binnacle. Exactly the same, yeah? And we're going to say that this lady here, yeah, she's annoying. She could have ginger hair. And she is going to be at the front of the boat. Now, she represents something steel. We'll say that you buy a couple of shackles of chain and we have them up on the foredeck, stored inside the anchor locker. They have a positive or a negative charge, depending where they were built, their orientation, their permanent magnetism. It could be the engines, could be whatever. But we'll say that we have this positive charge or a negative charge on the bow of the ship. Yeah, so it's a positive there, a positive there, a positive there, and a positive there, okay? This works better when you've got people pointing to north. But when the boat is pointing north, yeah, this positive charge, this annoying ginger-haired person, at the front is trying to sort of push that compass, isn't it? And it's actually going to have very little effect. Yeah, so the compass is going to point due north. When the vessel is going in an easterly direction, where will the compass still point to? The compass is always aligned with magnetic north. So as the vessel changes heading, the compass will continue to point at due north. Now the annoying ginger person is now on the pointy end of the boat. So the compass would have tried to point due north, but this positive charge is actually deviating the compass slightly. Hence, you're going to get a bit of deviation when the vessel's going easterly. Because there's positive charge, and if you've got your arm out pointing to north, if you've got positive charge in front of you, it's not doing much deviation. But if that positive charge is now pushing from the side, it's dead easy to deviate it off from its course or from its heading. When the vessel is now pointing south, it's behind it. And no amount of her nagging or annoying or whatever is actually going to cause it to deviate from north. So here you get very little deviation. Now, whoops. At 0 degrees north, there's very little deviation. When it's pointing that way, you get maximum deflection, maximum deviation. When it's pointing south, it's in line, so you get very little deviation. As it's now going westerly, that compass will keep pointing to north. So once again, if that's it pointing north, you've got this positive or negative charge either pushing or pulling. It'll either be pushing or pulling it away. Boats are all long and skinny, aren't they? You ever seen a wider boat than longer? No, all boats are long and skinny, hence why deviation cards are generally a sine wave. So at this point here, you're going to get maximum deflection. Hence why deviation is dependent on ship's head. That is shown in the petal diagram, and I'll put it on the screen. I think 1914 is before copyright law. So that should explain why it's so important that you know which way the vessel's pointing. Deviation is dependent on the ship's heading. That's a bit brief and a bit short, and I do expand upon that later in part B, but that should at least help visualize this petal diagram. This petal diagram carries on like that, and it shouldn't be something that's new. It's actually, or it was in the syllabus. It was positive charge or this negative charge depending on the construction of the ship, where it was constructed, the way it was orientated when it was built. But you've effectively, depending on the way the vessel is pointing in relation to the Earth's magnetic field, will depend upon the deviation experience. Now they've got permanent magnets, they've got soft iron correctors like Kelvin's balls and Flinders bar, and the healing magnet that does both. They try and reduce it to a minimum, but you're always going to have, going east or west, maximum deviation. So where would we find this deviation? You're going to have a deviation card. It's either going to be a tabulated formula or it's going to be a graphical representation. The back of the notes, you've got the one that I've made up, which is the one which I use all the way through for the questions that are part of the app, so you can start to get used to the likely style of question and the way they're going to present it in your exam. Everybody happy with that? As I said, it is a bit brief, but you're going to be at school, they're going to go through it for quite a lot. Uh-oh, it's stuck. If anyone ever sees my little boy, you can explain why. I hope it's helped a little bit as to why deviation is dependent on ship's head. The next part in the syllabus is that you have to show correct application of deviation and variation to compass course and bearings. Now, this depends on where you were taught, when you were taught. You could have been taught true virgins make dull company, add whiskey, or cadet, add yeast. I was taught true virgins. So true virgins make dull company, add whiskey. So if I'm going from true to compass, I add west. Therefore, if I'm adding, I take away east, if I'm going that way. If I'm going back that way, I must take away west and add east. So if I'm going that way, I add west, I take away east. If I'm going from compass to true, I take away west and I add east. So let's just do one of those together. Let's just say, we have deviation equals 3 degrees west and variation equals 2 degrees east. And we've got 0, 4, 5 degrees true, and we're going to convert that to compass. So true virgins make dull company, add whiskey. So variation is 2 degrees east, deviation is 3 degrees west. True going towards compass is add west, take away east. 45 less 2, 0, 4, 3, add 3, 0, 4, 6 degrees. Yeah. Let's go from 0, 4, 6 degrees compass, going towards true. So Cadbury's dairy milk, very tasty. It doesn't matter how you learn these. It doesn't matter if you've used the same ones, you've been taught something completely different. It doesn't matter as long as your answer is the same. Deviation we've got is 3 degrees west. So compass, add east, take away west. So that will be 0, 4, 3. Variation from the question is 2 degrees east. Compass to cadet, add east. So let's add that on, 0, 4, 5 degrees true. I always start to get a little bit nervous. Maths is not my strong point. Still to actually find my strong point. Chart work is definitely not one of them. Reducing the likely errors, I'm getting better at. Okay, that's what this exam's about, isn't it? It's about not making critical errors. We're going to practice that together. We're going to go through it until you understand it. So you have to be able to convert compass bearings to compass bearings. Good. We then have to know the difference, according to the syllabus, between a position line, circle of position, and transfer position. So understand the difference between a position and a position line. Okay, so here is the land, and we've got a church there. A position line would be a bearing of that, and it's there. That would be a position line. Yeah, you are somewhere on that. If you had another thing, you could take a 2-point fix. Yeah, you always have an arrow away from the object, and that would become a 2-point fix, and then you'd have the time next to it. Happy? So a fix, generally it's going to be a 3-point fix, so we'll just improve that slightly. We'll put that one there. So that is a fix. A position line is you're somewhere on that position or on that line. Yeah. To get a fix, you generally need a position line and a range. You can get that from a vertical sextant angle. You can get fixes from a running fix. You can get radar range and bearing, 3 radar ranges. Inside the notes, I've given you the differences there. Understand the definition of a DR, EP, and a fix. Okay, once again, this is coming from the Admiralty Manual of Navigation. Dead reckoning is the expression used to describe the vessel's course and speed. So we'll say that you have a positional fix here at 12 o'clock. A DR would just be your heading and your speed through the water, and that would be a DR at 13 100. You do not take account of leeway. You do not take account of tide. It is just engine revolutions and course steered. Okay? Happy with DR. So EPs, we'll say that you're here at 12 o'clock. There seems to be two different ways of doing this. I seem to prefer the second way, mostly because that's the way the past papers seem to want you to do it. So I surmise that that's the way the current, the real exam papers are written. In the fact that, well, we'll do the older way of doing it, which is where we'll say that this vessel is steering 090 or just above that. That is your heading, and then they add in the leeway. Now they actually do the leeway visually. So that would just be on there. And that's the leeway, which would then give you the leeway or the water track. And then from the end of that, you then add on your tidal vector. Now, there's nothing wrong with that, but to me that's always very confusing. So the way that the past papers, the way that I'm sure the current or future exam papers will be done, is where you do it mathematically. So I know in America they teach it that way, which is nothing wrong with it, it's fine. It's actually the way that the Admiralty always intended it. But we'll say that you're steering 090 degrees, true. And then we have a leeway. So the leeway is caused by the wind. The wind is blowing this vessel. And leeway is what did I write down? Leeway is the effect of the wind moving the vessel bodily to leeward at right angles to the course steered. So your boat's going that way, but the wind is causing it to just bodily go through the water sideways. So if we had 10 degrees of leeway, and the wind is coming from the north, and we'll say that that's your boat going along there, is getting blown down. So I always look at a compass rose. If I'm going 090, the wind's blowing down like that, I'm going to get pushed down. So it's added on. So the water track is 100 degrees true. And that is what the past papers and the way it's been set up is expecting you to write in your exam. The water track. So you're steering 090, and this becomes important when we do the beam. And then the leeway, for an EP, it has happened. You were steering 090 and the wind has affected you for the last hour. So it's past tense. It's happened. You didn't take account of the leeway. So you were steering 090, but your actual track through the water was 100 degrees. When we do courses to steer, that's futuristic. So leeway happens at the end. For an EP, it's happened to you, so we take account of it before we even get near a chart. So to explain that, we'll say that this is a fix at 12 o'clock. We were steering 090. We actually draw onto the chart the water track, the leeway track, the water track, and that is 100 degrees. Yeah, and that will have 1 arrow. We then take account of, we'll say tide. We'll say the tide was going that way. Tide has 3 arrows on it to indicate its tide. And at the end there, that becomes our EP an hour later. The line that goes from where you were at the beginning to there, that is your ground track. That is your course over ground, your speed over ground, your course made good, your speed made, anything like that, made good. It's in relation to the ground, and it has 2 arrows like 2 little feet walking along the ground. That is an EP. An EP takes account of leeway and tide. It is an educated guess of where we think we are. Our fix is where we are. Okay? So you need to be able to, according to the syllabus, to plot the ship's dead reckoning position using compass and speed log. We can do that. And then plot ship's estimated position applying set and drift. Plot running fixes with tide and leeway. We'll do that together inside the video. Understand there's been ground and water track. Yeah, fine. So let's do one together. Let's do this question here. I'm going to clean all this up and I'll just glare it out for a second and I'll glare it back in. So let's do one together using chart 5048. Take variation from the chart, deviation from the notes website. How do we do this? Right, well the first thing to do is to write down the relevant information. So at 0900, 2nd of Feb 2003, steering. Now it's important we know what we're steering because deviation is dependent on ship's head. 049 degrees compass at 12 knots. The following bearings are observed. Okay, we've got 3 bearings, so it's a 3-point fix. We've got Ballycotton Island down there, we've got Capel Island structure and Williamston Light. Okay, we've got a bit of tide, 180 degrees true. If it says southerly or something like that, it is true. If it says northerly, easterly, the wind, it is true. If they're referencing the chart, it is true. 180 true at 2.5 knots, and you've got 10 degrees leeway. Now, quite often you won't find the leeway until like second or third part through the question, so make sure you work out right at the beginning when you start if there is leeway and which way it is. So this is due to a northerly wind, so the wind is coming from the north, so it's going to be pushing our boat down. Are we doing an EP or are we doing a course to steer? We were there. Find the position in the future, so this is going to be an EP. First thing we have to do then is work out our compass error. So we are steering 049 degrees. Compass, Cadbury's Dairy Milk, very tasty. Deviation. So we're going to find deviation from our compass card or deviation card. So let me get one. And you're going to find this at the back of the notes or in the download section, www.fredsapps.com, and you're going to download that so you can work slowly, gently with me. Press pause if I'm going too fast. 049 compass, very close to 050, so that's going to be 3 degrees west. Cadet, add east, take away west, 49, 48, 47, 46, so 046 degrees magnetic. Variation, so whereabouts on the chart are we? We were here. So we have in 1994, and I do suggest that when you're working through this, that you have a template that you follow each and every time. If you have a template, you tend to get looking for the right things. You're going to find the compass error. You're going to apply the compass error to all the bearings. You're going to see there's leeway. If you have a system, it does seem to reduce the odds of getting things wrong. So 7 degrees, 25 west in 1994. The year of this question is 2003. So 2003 less 1994 is 9 years. So we have 9 times, what's it doing? It's going 8 minutes east. So 9 times 8 is 72. Less 60 is 12. So it's 72 minutes or 1 degree 12. East. We're west of north and we're going eastwards. So it's going to be minus to give us today, or 2003 variation. So 25 less 12, 13. 7 less 1 is 6. 6 degrees, 13 west. So use, and I would suggest working to the nearest half degree. So 13 is closer to 6 than 6.5, so use 6 degrees west. Happy? Happy? 6 degrees west. Cadet, add east, take away west. So that makes that 0, 4, 0 degrees true. So we are steering 049 compass, but that is 040 true. So our compass error, the error of the compass for this heading, is going to be 3 plus 6, which makes that 9 degrees west. That error we apply to all the bearings that we've taken whilst we are steering 049 degrees compass. This bit confuses people, and I know why, I understand why. Because you've not seen how, when they wrote these questions, they took the bearings. Yeah, we're obviously using a magnetic compass. And a magnetic compass is fantastic. It doesn't need power. Yeah, it doesn't need power. It looks pretty. It's never going to go because it will get you home if everything else fails. Electricity, water, especially salt water, does not mix. So how do we take a bearing though with a compass? Well, we can have azimuth mirrors, we can have azimuth circles. They generally go on gyros though. So a pylorus would be a good way of doing it. Now, I happen to have a pylorus. So that is a pylorus. Now, on YouTube, there's some videos of where I've explained how they work. There's ship's head. So we'll imagine that ship's head is, we'll say, that way. Okay? So our vessel, where's Timmy's boat? Our vessel is steering that way, and it's steering 049 compass. So we'll say there's 90, there's your north, there is 049. Yeah, and it's pointing that way. So we can use this two ways. We can either take relative bearings or compass bearings. So radar, that works for two things. This works for two things. There are two things the OOW has to do on watch. One of them is avoid other ships. And for that, to work out if there's a risk of collision, we take a series of compass bearings. If the compass bearing remains constant or does not appreciably change, then risk of collision is deemed to exist. Or if the CPA is 0, or if you look out the window and the window frame, the boat stays on the window frame, you're likely to hit the bugger. This can do relative bearings, which is exactly what you want to do for collision avoidance. Or it can do compass bearings. To do compass bearings, you undo the clamp there and you turn this around till it matches the ship's head. Yeah. So there is 0 and we're steering 049. So if I bring that round to 49, now the numbers, this is antique. The numbers are slightly done, probably not coming up the best in the camera, but I've got 0 up to all the way around to 360. So we'll set up to 049. On the side there, there's a clamp. and I'm going to clamp that tight. So the ship's head is reading what the compass is meant to be reading, or what the helmsperson should be trying to steer. So I shout to Timmy. Where's Timmy? It's Timmy's wife. Timmy is driving the boat. Timmy's wife. Timmy, let me know when we're on 049 compass, mate. Now, when the vessel is on 049, I can take, using this Polaris, compass bearings. So in this case here, I'm going to take a compass bearing, or a bearing, of Ballycotton Island, and it's bearing 273. Then I'm going to take another bearing at 306 and another one at 333. Yeah, to do that, head down, I look through the sight vanes, and I get a nice bearing. That is all based while the ship is steering 049. So while the ship is steering 049, I can take a bearing, sorry about the squeal, I can take a bearing reference to the compass. Therefore, it's the deviation and the compass error that is going to be based to all of those bearings. Yeah? If I was using a gyro, it would be based to the gyro error. That is why, depending on what the ship is steering, will affect the deviation and therefore the compass error. So you apply the compass error for the ship's head. I think for me, once I realized how these bearings were being taken, it made sense, because it's that compass that you're referencing it to. Yeah, hopefully that's helped a little bit. So I have all the props here on the Isle of Wight, because I'm sure that you all have a Polaris on board, don't you? You use this on a regular basis to work out if you're going to hit a boat and to do your 3-point fixes. I know that for me, I may not have used one until I became a teacher. So, or at least not something like this. Hopefully that will help you understand why it is we work out the compass error for the main compass, and then we apply that compass error to all of our bearings that we take while we are steering 049. If we change our heading, then we've got to work out the new compass error. Put Timmy's wife away. Happy? So the compass error, we're going to apply those to our three bearings. So we had Ballycotton Island, and that's 273.5 compass, and Capel and Williamston Light. So Capel Island is 306 degrees compass, and Williamston Light is 333 degrees compass. And we have a compass error of 9 degrees west. Cadet, add east, take away west. So 273.5 less 9 gives me 264.5. 2, so that equals 264.5 degrees true. 306 less 9 is 297. 333 less 9 is 324 degrees true. Everything that happens on the chart has to be true, reference to true north. So I've just converted all of those compass bearings to true. So now I can put them onto the chart and I can work out where I am at 0900, completing part A. Your tools. You need to look after your tools. Your tools look after you if you look after them. So, how do you use this? You want to be accurate. What you do in real life really is up to you, but To get through this exam, you need to be accurate. As accurate as you can be. So you need a sharp pencil and you need to use the tools correctly. 264.5 Ballycotton Island, that's there. So we're looking for 264. So 264 is there. Now I don't use the edge because there is error in that. What I use is this black line. These black lines are there for a reason. So if I line up 264 there, yeah, there it is, and I put it through the center there on that black line, I can get exceptionally accurate. And it must mean if 264 there, it must be the other side of there. So I've just sort of compared that number with that number and made sure I've gone through the center. That is 264, I need 264.5. 264.5 degrees. Take that up. To Ballycotton Island. So walk it up. This is why you need good ones with little bits of cork and everything else. Don't get the cheap ones, not worth it. It's an expensive exam. Ballycotton Island. Then you draw a line away from it. Nice solid manly line, you're very confident on this. And that has an arrow on the end to indicate it's a position line. Second bearing, 297 to Capel Island. That'll be off the structure. In preparation for this, I googled it. It's just a little structure. Where would you find information on what the symbology means? It's 5011. I don't know, it's chart 5011, a nautical publication 5011. I can never remember. Could be your homework. 297, so 567. 297. Yeah, please be accurate when you do this. It does make a difference. Trust me, I've done all of these like 5 times. There's 10 questions I've worked through to make sure I've got them right. It's 5 times to make sure I get them the same answer at least 2 or 3 times. A thickness of a pencil does make a difference. So Capel Island. Nice little arrow on the end, and then 324 of Williamston Light, which is there. So 324. I am looking at that end, it should all line up. I would be surprised in your exam if you didn't get a perfect 3-point fix. So if you don't get a perfect 3-point fix, do have a look back at your working. Yeah. So that is a fix. A fix always has a time next to it. So that was at 0900. Question was, find the position at 0900. So, to find your position, how stupid would you look if you got that right and then you can't do Latin long? Yeah, I can imagine me, to be honest, doing that in my exam. It's just something that would happen, isn't it? So I'll put that just there. We will come back to that. So it's not away, it's just there. So part A, position at 0900 equals, so where are we in the world? 51 degrees 20, so it's going to be 51 something. So 51 degrees. I'm then going to line this up. I'm using my black line here. I'm then going to walk that up. And I'm not using the edge, but I'm actually using the black line again. It needs to be a bit more over that side to start with. So, line that black line up. and I've walked that up. So that is 45, that's 50. That's 2, 4, 6, decimal 6 north. That is how accurate you have to be. Use that black line, that's why it's there. Yep, happy? You might find that we disagree. Especially there. It's 0.4 north. 2, 4. Yeah, always double check your work. 51 degrees, 50 decimal 4 north. And then are we east or west? Where are we in the world? 8 degrees. We can sail, so we'll be west. 7 degrees west from Greenwich. So it's going to be equals 007 007. $30, $40, $41, $42, $43, $43, $41, $42, $43, decimal 2 west. Yeah. So part A, find the position at 0900, 51 degrees, 50 decimal 4, 007 degrees, 43 minutes, decimal 2 west. You should have got the same answer. We should be fairly similar with that. Sometimes the charts aren't the best, but if you bought the charts, so you've been given the charts, there's no reason why we should disagree on that. Part B. Find the position at 10 o'clock. Okay, so we are going to be steering 040 true. So we're steering 049 compass. So steering 049 compass, which means we're steering 040 degrees true, but we've got some leeway, don't we? So the leeway has been happening to us. This has happened. So leeway, this is an EP, so it's already happened to us. It's past tense. The leeway was 10 degrees due to a northerly wind. So we're steering 040, the wind is blowing us, so it's going to be going up. So it's 10 degrees and it's plus. I look at a compass, I'm steering that way, the wind's blowing that way, I'm going to get blown that way. So it's added on. Keep life simple. I know there's sayings, I'm sure there's compass best. I just look at a compass rose and know what would happen in the real world. It would push me that way. That way is add. So that's 050 degrees true is what I've achieved as my water track, leeway track. Yeah. So 050, I've got tide of 180 at 2.5 knots. Where am I at 10 o'clock? Awesome, I can do this. So 050, using the edge, the whole number there, so that's good. And I'm going that way. And how fast am I going? 12 knots. So that's 10, that's 12, so it's about that long. Measure it off. So I have a compass there. I'll stick it on. Which side is better? I suppose this side is better. 45. 11, that's 12 there. Oh. So I'm just holding on this side so you can see it. 12 knots. Stab it in. Just double check it because it'd be annoying to get it wrong in front of everyone. Measure that with my set of dividers. 12 knots. Yeah, so that's 12 knots there. That's my rudder track. So it has one arrow. Just clean off the end there so you don't get confused. At the end of my water track, I'm going to add on my tide. It is 2.5 knots at 180. So 180. Yep, 180. Take that across, 2.5 knots. Measure tide of 2.5 knots. Because this is a Mercator chart, I have to use the edges the same height as where I am because of the distortion. So that's 2.5. It has 3 arrows, and that becomes my EP at 10 o'clock. I can then do my ground track across. Yeah. And that has 2 arrows. What is the position? So position at 10 o'clock. It's going to be 51 degrees. It's right in the middle. It's annoying, isn't it? So, using the scale there, that is 51 degrees, 55 for 6, so decimal 5, 55 decimal 5. Yeah, decimal 5 north. Okay. Our westerly. .007 30. So it's going to be that side of 30. And that is, excuse me, standing up. $25, $26, $27, $28, $28.244, 28.4 west. So position at 10 o'clock is 51 degrees, 55 decimal 5 north. Give or take a little bit. We could have a little bit of margin with our pencil, but not a huge amount. And then 007 degrees, 28 decimal 4 west. Happy. Next thing we need to do is part C. The position when Ardmore Head was a beam. Where's Ardmore Head? That point there. Okay. A beam. A beam is 90 degrees to ship's head. A beam is 90 degrees to ship's head. And it's important that you write that down. That is worth 6 marks, just writing that down. It will also mean that you get the right information. So we are steering 040 true. we were achieving 050. So you go back to the question, 049 compass is what we were steering, which is 040 true. So our ship's head is 040 degrees true. I don't care for the water track, that's what we achieve through the water. Yeah, it's not going to look right. Our ship's heading is 040. 90 degrees to that is the beam. Yeah, that is the beam. So 040 less 90 is a hard number, isn't it? 040 is that way, less 90, so it's going to be about 315 or 310 or 320. Now my brain struggles with that, so I actually add on 360. So 360 plus 40 is 400 degrees. Now that's the same as 040. Yeah, I am 40 degrees past 60, therefore it's 400. So that now less 90 gives me 310. Yeah, that, sorry, minus 90 is 310. That is the beam bearing. Now I don't mind if you want to do the heading is 040, and on the piece of paper on your chart you just do that. You use the end of that. Yeah, there's a nice line there. You just confirm that that is 310. That is 90 degrees. 040 less 90. Some of you just instantly go to 310. Me, I always have to add it on to 360. If it was going the other way, it would be easy because the number would work out. But 360 plus 40 is 400 degrees. 400 degrees less 90 is 310. Yeah, you can see it visually, you can see it mathematically. So 310 is the bearing, that's in true because working on the chart, to the abeam position. That's the abeam to the ground track. Our boat was steering 040. It achieved 050, but its course over ground was that line. Yeah, it actually did that. So it was there. So the abeam is the abeam position to that ground track. So 310. Let's take that up. To Ardmore Head. That's where it cuts across the ground track. That there is the abeam position. Yeah. What time is it when it's a beam? Time. So distance equals speed times time. Or you might have learnt distance, speed, time. Depends how old you are, where you were taught. I want to know time. So that's distance divided by speed. I put my thumb over the time. It's distance divided by speed. So distance divided by speed. So I need to know the distance. The distance to the abeam position. So I measure that as 5.5 miles. 5.5 nautical miles. Can also be written as that. Yeah, so from now on I'll write it as that, if that's okay. Speed over ground. Because it's the ground track, it's something in relation to something that's on the ground. So I don't care what I'm doing through the water when I'm referencing the ground. So it's speed over ground. So when it says a beam, write down speed over ground equals. That is important. So my speed over ground, what equates to my course and ground speed? My course made good, my speed made good, is that line with the 2 arrows. That is how far I will travel in relation to the ground in 1 hour, isn't it? So I measure that. Yeah, take it from this side here. And that is 10.5. knots. 10.5 knots. I have travelled 10.5 knots in relation to the ground, therefore my speed made good, or my speed over ground, is 10.5 knots. Therefore time is distance divided by speed. Time is distance divided by speed. So distance 5.5 divided by 10.5 is 52 times 60 minutes, 31.42 minutes. Give or take a little bit, it is going to be just under 31.5, so 31.5 minutes. Therefore, ETA equals 09, it was 9 o'clock we started, that was 9 o'clock, 09, 31.5. 09:32, 09:31, it's fine. I'm a bit over the top by going to half minutes. But 09:31, 09:32. That is the time of arrival. That is a standard question. They could be courses to steer, they could be running fixes, they could be several variants of that. That was our first EP that we've done together. We also need to know how to do a running fix, a course to steer, and how to find your position. So let's do a course to steer. We'll say that you are here in this position at 12 o'clock. The first thing you would do is you would work out where you're trying to go. And we'll say that we are, there's the bit of land, we want to go to a waypoint due south of that bit of headland there. So what you would do is you're going to draw on your ground track, yeah, and you're going to extend it all the way through and beyond. That has two, because that is what you're trying to do as your intended ground track. You would then put on your tidal vector, so we'll say in this case the tide is heading this way. How many arrows would that have? It would have 3. And then from the end of your tidal vector for an hour, or whatever the time frame is that you're working in, you would then arc off your boat speed. So we'll say that your boat speed is that. From the end there, you arc it off. Yeah, so I've got it like that. I've measured my boat speed, I arc it off, and we'll say it comes to there. You then join that up, and that becomes your water track. Yeah, so that's your water track, and we'll say that that is water track of 0, 4, 0 degrees true. I'm just going to work in true. That is what you want to achieve through the water. Now, we're always going to have a bit of leeway in these exam questions. We'll say the wind is coming from the north. How would you counteract that? Well, we haven't left yet. This is future. We haven't done it yet. So you're going to tell the helmsperson to steer into the wind. So in this case, we're going to steer, we'll say the leeway is 10 degrees because of this northerly wind. We're going to steer 10 degrees high. So looking at a compass rose, it goes from 0 right round to 360. So it's going to be minus. So leeway minus 10. So our course to steer is going to be 0, 3, 0 degrees true. Okay, happy? We would then need to convert that from true to compass, because it's going to ask you for a compass course, so you'd have to do true virgins make dull company, add whiskey. And you'd actually have to draw a third column. This is something that everyone makes a little bit of a mistake on. We'll say it's 0, 3, 0 true. Let's use that as our example. I'm just going to rub this out. And 0, 3, 0 is what we're going to steer, okay? We want to steer 0, 3, 0 degrees, and that is true. So true virgins make dull company, add whiskey. So from true to compass is add west. looking at the chart, we'll say that variation is 4 degrees west. So true virgins make Dole Company add whiskey, so that's add west. So it's going to be 0, 3, 4 degrees magnetic. Okay, at this point, you now need the deviation card. Yeah? So you get the deviation card out, and we're looking for a magnetic value. We're not looking for a compass value. So if we've got compass, and then we have deviation, then we have magnetic. Yeah? And these are the columns. So in real life, you actually would have magnetic written down there. You'd have like a third column. So you have to produce this third column. Because if you took 0, 3, 4, you would assume it's between 0, 3, 0 and 0, 4, 0. And you may take the wrong value because we're trying to find what the compass is. We have the magnetic value and we're looking for the deviation to get the compass. That's going to hurt some of you. I appreciate that. It seems to have always taken a lot of time to go in. So rewatch that bit. We are going from true to compass. We go from true to magnetic because we know the variation from the chart. That gives us a value for magnetic. We need to work out the deviation to get to the compass. If we were going from compass to true, we would take the compass figure and get the deviation. But in this situation, we're actually going from true to compass. So we need to work out. So we'll say 0, 2, 0. I'm just going to reproduce this deviation card. 0, 2, 0. The deviation would be 8 degrees west. 0, 3, 0 would be 8 degrees west. And 0, 4, 0 would be 6 degrees west. So in your exam, you're going to draw a third column if you're going from true to compass. So if it's a course to steer, you'll have to do that. So cadet, if we're going from compass to true, we add east if we're going that way, and we subtract west if we're going that way. So 0, 2, 0, we've got 8 degrees west, that's going to be minus, so that will be 0, 1, 2 degrees. Yeah? 30 minus 8 is 0, 2, 2 degrees. 40 minus 6 would be 0, 3, 4 degrees. Hello? That's the figure that we're looking for. So the correct deviation for a magnetic value would be 6 degrees west. Yeah? If you went the other way, you would have got taken the same value, but you would have done it wrong. You must show the examiner that you appreciate that you're working from true to compass. Therefore, you must draw in this third column. Yeah, you'll see that I've done it from when I've been doing my working. I draw it in pencil and I fill it in. When we do these on the video, you'll see what I mean. We'll do it in practice inside the app itself. But that should be something that's made clear to you during your course. So therefore, the deviation that will be affecting our magnetic compass if we were steering 0, 3, 4 magnetic would be 6 degrees west. True to compass is add west, so that should be 0, 4, 0 degrees compass. Happy? We are therefore going to tell the helmsperson to steer 0, 3, 0 true, which on his magnetic steering compass would be 0, 4, 0 for that heading and for that part of the world at that time. Happy we've had to do a course to steer. We will do a lot more of those together inside the app. Next then, let's talk about, we've done DRs, we've done fixes, we've got to still do a running fix. So we'll say that there's the bit of land there, and we've got a single point. Let's make it a church. Yeah, there's the church there. And we're going along, and we can see this church out of the port window, and we can get a position line. So we take a position line on it. Yeah, so we draw our position line on, At the end of all of our position lines, they have 1 arrow. And then we're going to do an EP. We didn't know at this point that we were going to be able to convert this to a running fix. So we choose somewhere that's sensible on it, and we put our water track, so that's taking account of leeway, on like that from any position. We'll label it. We'll then put tide on. We'll say the tide is going due south. So it's got 3 arrows. And that gives us an EP an hour later. We'll say we were at 1 o'clock. Yeah. Gives us our ground track there. We can just always extend that through. So that's our ground track, our course made good, our speed made good, whatever terminology you prefer. But what we're amazed at is that at 1 o'clock we look out the port window and we can still see the same church, and we take a second bearing. This allows us to do a transfer position or a running fix. So we take that second bearing, and where that EP crosses with the first one, the transferred line, is going to be our fix. So you just parallel that across. Yeah, you put 2 arrows on, always from that direction, to show it's from a terrestrial body. And that will give you now a fix at 1300. Happy? It is. I'm always amazed when you have 12 students and they all start in a completely different spot and it works out that everyone's in the same place. I think it's amazing. I know it's probably just geometry, but I find that to be still very impressive. The key then is they will ask you what time are you going to be a beam of, we'll say, point A. You would then transfer that ground track up, because that's what you actually achieved, which means that at 12 o'clock you were there, at 1 o'clock, and assuming that nothing else changes, that will be your ground track. So let's label that with 2. And the abeam position would be a beam. A beam means 90 degrees to ship's head. So you go back to the question, you find out what your ship was steering. In our case, it was 040 true. And then you would take 90 degrees off, or add 90 depending if it's at the port window or the starboard window. The abeam position always seems to be the third part, and then they're going to ask you what time do you arrive. ETA is all in relation to the ground, because what time are you going to arrive at this point here, this abeam position, it's fixed to the ground. So you need to know your distance to go, which would be that, yeah, so that'd be your distance to go, and your speed made good, your speed in relation to the ground, is represented by that. So it would be distance equals speed time, so time is distance divided by speed, so it would be, I know we'll say that's 6 miles divided by 8 knots, so it'd be 45 minutes. So it'd be 45 minutes after 1 o'clock. Appreciate that was a bit quick, but that should just be enough to get you going. We'll do some more together inside the device, inside the app. This is a quick edit to add in a new type of position fixing question. It's been asked recently in just one exam. If it becomes more used in the exam system, I will add more worked examples. However, in the meantime, it's come up once. I want to show you the question, and then we're going to do a worked example similar to this question. So question 1 was a range of 5 miles from a lighthouse at 10 a.m. and then an hour later, 5.1 miles from a different lighthouse. Course was given as 232 true and a speed of 10.5 knots. Tide was 170 at 2 knots, and they asked for position at 11 o'clock, 10 o'clock, and a course made good. It was a running fix, and we were supposed to transfer the range to 11. I knew it was a running fix, but couldn't get my head around it, is the report from one crew member. We are going to do a worked example on chart 5056. You should have it there in your collection of charts, and hopefully it will make sense. And if this question comes up again, you'll be in a fantastic spot to answer it. It's an EP with one extra step. I'll do it on my iPad first, just so I can explain the concept, and then we will do this worked question. So here is the headland with 2 conspicuous points. The first one will mark as being red. So it's a radar range. Yeah, it says one of the students reported back it was restricted visibility. The other one didn't say that. I'm always getting sort of second-hand information, which is good. I don't want to see the original questions. I'm happy to work with an understanding. I then create my own questions, and we can then make sure that any question that is presented to us, we can manage. So we have a first range of this, and we'll say that that is 5 miles or X amount. Then we have our second range an hour later of this green one. So we'll say that that is, I know we can make it a bit bigger, we can do whatever you like. We'll say it's, I think in my thing here, it is 6 miles, so slightly bigger. We then are going to work from the center of our first range. Now, normally we know that at 10 o'clock, our boat was somewhere on this red range line, wasn't it? A circular position line. So the easiest way of dealing with that is to remove that range, and we'll add it in later on as a transferred radar range. So we're going to work from the center. So it's 207 compass. We need to convert it to true. We'll do that together in a second. But we'll say it's about, I don't know, 207 is about there. And then we've got a bit of tide, which I think was 220. So we'll put it there. Make it a bit longer. And we add our 3 in. Now that gives us a position there. Now it's not a true position, not a real position, it's kind of an EP, but it's based off the center of that first radar range. We are now going to transfer our radar range from starting at the center of that red bit. We are out by that much, aren't we? A radius out. So if we were to duplicate our first range, that's that first range, and I'm transferring it down here to the center of that red bit, you will see that we could have been, well, we are now at 11 o'clock in one of two places. We are either here at 11 o'clock, which is where we are, or we could have been there at 11 o'clock. We're not on that one there. I'm going to remove that one completely. The reason I know we're not there is because our ground track will allow us to calculate back to where we were. So that line there, I've just put on, from the end of our EP back to the center of the red circle, is our ground track, our course made good. So if I copy that across, if we were there at 11, it means that 10 o'clock we were there. If we did it from the other one, where it could have been, we were on the land. We're not likely to have been on the land. So we can determine that at 11 o'clock we were here, and that at 10 o'clock we were there. And this line there is our ground track. Therefore at 10 o'clock we work out our Latin long for 10 o'clock, and that is the correct answer. Then at 10 o'clock, an hour before, where were we? We can work out the Latin long. And our course made good is the line with 2 arrows. That's the theory. Do you want to do a work one together? Let's do it. Let's do this one that's there on the screen. I want you to take a screenshot of that or write it down, or if you're really worried about it, you can send me an email and I'll send you that question. I can send you more questions if you feel that you want to do a few more. I can make them up and I can send you through the answers. Using chart 5056, the first thing I'm going to do is on my piece of paper, I'm going to write down chart 5056. I'm going to take all the salient information from the question. So it's the 10th of May, 1994. And we are steering 207 degrees compass. I must have a speed there somewhere. So later on, at a speed of 8 knots, at 8 knots. Tide is 220 at 2 knots. So when I'm going through these questions, now later on when we do the worked examples of chart work, I'll explain my layout slightly better or over and over again. But I think it's important that we take all the salient information from the question and we put it into our own writing in our answer sheet. So if we've made a mistake in copying, the examiner can see why we've made the mistake. So at 10 o'clock, The first radar range was Berry Head at 4.8 nautical miles. Now a little line like that is a nautical mile. Then at 11 o'clock, start point at 6.0 nautical miles radar range. So we've got two radar ranges. We've got our vessel with our course steered 207 compass at 8 knots and tide. The first thing we need to do is convert our compass to true. So it is 207 degrees compass. Cadbury's Dairy Milk, very tasty. Or those of you who did Yachtmaster, it could be True Virgins make dull company add whiskey. Yeah, going that way. Cadet add east. True Virgins make dull company add west. We will go through this over and over again, how you convert the deviation and variation. So the deviation, where am I going to find the deviation? On the deviation card. So 207 is very close to 210, so it is 7 degrees west. Trust the calculator. 207, I can do this one actually, less, because adding east, if you're going from compass to true, less 7 is 200 degrees. Now the variation, I'm going to look at the chart for the variation. So in 1979, the variation was 7 degrees 40 west. Now we are in the year according to the question, 94. So 1994 minus 1979 equals 15. Therefore, there is 15 years of annual change. The annual change is decreasing 5 minutes. So decreasing, so it must be east. 5 times 15 times 5 is 75 minutes. So 75 mins minus 60 is 1 degree 15 minutes. Because 75 minutes is 1 hour and 15 minutes. And that is east. Therefore, we take it away. Now, don't panic if you're not following this variation. We will do this together at least 10 times in the worked chart work examples. 40 minus 15. 40 minus 15 equals 25. 7 minus 1 is 6. Well, I even wrote it down wrong. So 6 degrees 25 minutes west. So we are going to use 6.5 degrees west. So 6.5 degrees west. So that's take away 200 minus 6.5 is 193.5 degrees true. So our ship was steering 193.5 degrees true. Should we put it onto the chart? So the first thing we're going to do is we're going to get our compass and we are going to mark on these ranges. Okay, so the first range is 4.8 nautical miles from Berry Head. So I'm going to get 4.8, my compass. Yeah. And I'm going to take it off the edge and I'm going to draw a circle onto the chart. I'm going to label that as it's a range with 1 arrow either side of the arc. The second range, an hour later, is start point at 6 nautical miles. So I go to 6 nautical miles from start point, and I draw a second range on. Label that. Then I'm going to put my course steered from the center of Berry Head. So it is 193.5. So 193.5. I'm pretty sure in real life you would not work to half degrees, but in this exam we are going to. Okay, so bury head, 193.5. For how far? We are going for 8 knots. Okay, so that has 1 arrow, as it's my leeway track. I'm going to measure off 8 miles. So that's 5, 6, 7, 8. So that's 8 knots. So from bury head, I'm just measuring from bury head. So that's 8 miles. Now I want to do my tide. My tide was 220. miles. So I measure off 2 miles. Extend that line slightly. So that position there is my, it's not an EP, it's not a DR, it's just a mark on the chart. What I need to do now is transfer that first range onto that position, and where it cuts the second range is my fix. So that was 4.8. So measuring 4.8 across. And we're going to just check that still matches bury head. I haven't made a clerical error. That's fine. So from there, we are now going to draw. Now it's going to cross the line 2 places, isn't it? There, which is not likely because it would be aground, and there. So that is a transferred range, so it has 2 arrows, and that is our fix at 11 o'clock. To work out where we were at 10 o'clock, we transfer this line, this ground track, which is correct, across to there. So there we are there. That means that that is where we are. That is our ground track there. 1, 2. So that is our position at 10 o'clock. And that's our position at 11 o'clock. We're going to need to know that ground track, so we'll just write that down. I'll discuss in further videos how you use your parallel rules. But I'm using this magnified line on the side. So I'm getting a course made good of 198. So 198 degrees true. We're now going to be looking for our position. So latitude, I line my parallel rules up with that line there, so I know I'm getting it straight. Take it up. My solid line there. And then the same for my longitude. Lining it up on the edge there, nice and straight. So, to answer the question in the exam, position at 11 o'clock. So, position at 11 o'clock is 50 degrees. 2, 4, 6, 7. 50 degrees, 10.7 north, and 003 degrees, 29.9 west. Okay, therefore my position at 10 o'clock was, so I've taken the ground track back So I know I'm now there at 11 by using a transferred circular line or a transferred circular position line, running fix with ranges. And I've taken it back, and at 10 o'clock I can work out where I was. So on the left hand side, so I'm just using this line here to line everything up. Get it up. So it's my latitude and my longitude. Now I use this here, so I'm lining my parallel rules up this black line there on that edge. So position at 10 o'clock was 50 degrees, 20.0 north, and 003 degrees, 25.0 west. Course made good. Course made good was 198 degrees true. Now, I need to know my compass error, because I would have thought they'd want that in compass. So 7 plus 6.5 is 13.5. So compass error equals 13.5 degrees west. So 198 true, virgins make dull, company add whiskey. So 198 plus 13.5 is 211.5 degrees compass. Okay, so our position at 11 o'clock where we are now is 50 degrees 10 minutes decimal 7 north and 003 degrees 29.9 west. Position at 10 o'clock an hour ago was 50 degrees north, 20.0 north, and 003 degrees 25.0 west. Course made good with 198 degrees true and 211.5 degrees compass. I don't know if this question will come up again or what will happen. I'll be interested to see what happens with it. If it did come up though, I'm hoping that this will make you feel more comfortable. Do ask your lecturers, and if you want some more questions to do, let me know which charts you have, and I will do a couple more questions, and you can email me your answers and I'll let you know if they're correct. If this question lasts more than a couple of, comes up again, I will add it into the main app as some new questions. Good luck with your nav and radar, and I'll speak to you once you've passed your exam. Next then, looking at the syllabus, understand the difference between ground and water track. So depending on the arrows, one is speed through the water and what you're doing through the water. The other is what you're doing in relation to the ground, either course made good, speed made good, SOG, COG, what you and I would see on the GPS. Then we got fixing position by compass bearings. I'm pretty confident you can do that. You take 3 position lines, where they cross, that will give you your fix. Ranges and bearings, yeah, you could have a bit of land, and there's a rock there, and on your radar screen you take a range and a bearing from that, so you know that you've got a bearing going there and a range of X amount, put arrows on the end, where that crosses will give you a fix at 12 o'clock. You could have 3 radar ranges, in which case you've got a bit of land that's prominent, we'll say there, a rock that's there, and another jetty or something there. You get 3 ranges, and we'll say that X amount. You then get your compass, and you arc off each of those ranges, and you should get a nice 3-point fix, or something like that. And that one there would be like that, and that therefore is your fix. We'll do a couple of those together inside the app as well. Dipping distances. You can do that 2 ways. You can do it mathematically, or you can do it via the tables. In your exam, if they ask this question, I would imagine they're going to give you the tables, because it's the way that you would do it at sea. Well, at least it's the way I would do it, see? It's very simple if you do it via the tables. You can do it mathematically. It's the distance equals 2.08 divided by the square root of the height will give you the c miles. Yeah, it seems fair enough. However, to do it and to explain it quickly and efficiently for you, we say that you can see this light, and you can see it out the window. Yeah, and we'll say it's in the daytime, and you can see the top of the light. So imagine that's the light. You're going to take a bearing of that. Yeah, so you've taken your compass bearing or your gyro bearing, and what you want to do is, as it dips below the horizon, I don't know where the edge of my camera field will be, but I imagine it's about there, but we'll say it's there. As that dips below the horizon, at that moment you take a bearing just before it disappears, and at that moment you write down the time. Or as it appears to a dip above the horizon, so it either appears above the horizon, you can see this loom coming over, and then you see it, bosh, that second is when you take the bearing, you write down the time. So we'll say it disappears, so there it is, it's going below, it's a very wavy day, bosh, it's gone. The time was, it's 10:15, so it's 10:15, the bearing of it was 045 degrees true. The concept behind this is that if you know how your height of eye, because the world is round, you can see a limited distance to the horizon. Now, I'm not very good at sketching this, but we'll say that you are there, that's you. You can see that far there, we'll say that's the sort of limiting factor. So the other thing that's going across the mountain or the light or the church or whatever it is that you're looking at appearing or dipping below the horizon, it can see a certain distance too. So you've got this distance here, which is x, and then you've got this distance here, which is x. So it will depend on the height of the eye. So the moment it appears or disappears from the horizon, that is said to have occurred. Therefore, if we could work out that distance and we could work out that distance, we could add the two together. So if you're watching this inside the app, you'll see that I've given you a couple of extracts there, and I've given you a worked example. We'll do the worked example there. We'll say that your height of eye is 12 meters. The height of the light, how would you find out how high the light is? Well, you're going to go into the chart, or the Admiralty list of lights, the green spine, and it will tell you the height of the light above mean high water springs. So we'll say it's 40 meters. You can then go into Norries. So I've got a copy of Norries. Where's my Norries gone? I have a copy of Norries here. You go to the front of the book and you're looking for distance of the sea horizon. So page 459. And there's a beautiful table there, and it has their height and their distance. So if the height of eye was 12 meters, you look for 12 meters, and it says it's 7.3 miles. That little symbol means miles. Then we've got 40 meters, so let's have a look what 40 meters is. That's 13.2. You add those two together, and that's 13, that's 20.5 nautical miles. So you could see 7.3 miles. It could see, if it was someone on it, it would see 13.2. Therefore you add those two together and you've got the distance from where you are to where it is as 20.5 miles. Therefore we've now got a bearing of 045 and a range. So we have a position line and a range, which allows you to produce a fix. So that's called dipping distances or distance of the sea horizon. There are other ways of doing it, there are other tables, but that to me is the easiest and simplest way of doing it. If you were asked that question in the exam, they would either give you a copy of Norries, which I notice the schools now have all got 12 in their shelves, or they might have an extract inside the Tide tables. Next one, vertical sextant angles and horizontal angles. So a sextant, that's scary, isn't it? I said the word sextant. You are going to have to explain that for the oral. So if you've got the experience or the time, the opportunity when you're in class for Nav and Radar, do pick it up, use it, look at it, ask questions about it, because the more you can be familiar with this device that measures angles, the better placed you will be. I'm not going to spend forever on it because I'd rather do worked examples with you on that. But it is. Vertical sextant angles is nice and simple. You take a bearing of a light. Yeah, so you take the bearing, that will give you a position line. You now need to work out your height. So we'll say that there is the light, yeah, or the structure. There's you standing on your boat, holding a sextant, and you're going to measure the angle. Yeah, so that is going to give you Pythagoras. If you know that distance there, you know that angle, you can do, I think it's, I can never remember if it's cosine theta, tan, or whichever one it is. Or you can go into Norries again. So if we've got a bearing, we know the height of the object from the chart. It's above mean high water springs, and you can measure the angle from the top of the object to the water. You've got an angle. So we'll say, I don't know, 2 degrees, 35 minutes, and we'll say that that is 99 meters high. Inside Norries again, we're looking for Norries, we're looking for vertical sextant angle, page 462. And it's ranged by vertical sextant angle. At the top there, you've got the height of the object, so in our case it's 100 meters, so let's find 100 meters, or 99. Here it is, 100 meters. And then you have degrees and minutes, and I'm sure that's not going to come up in the cameras, but it says degrees, minutes, so this is the observed reading, the angle from the sextant. So we had, what do we say, 2 degrees 35, so 2 degrees 35, 2 degrees 35, on the side, both sides, it's a range in miles. That is 1.2 miles. So that has given me a range of 1.2 nautical miles. We took the bearing of the object, 045 degrees true. We've got a range of 1.2 nautical miles. That will give us a position fix. Yeah, happy? Good. There's nothing scary about it, especially in the exam. They're going to tell you to look at an object on the shore. You're going to get the height of the object. They're going to give you the subtended angle, just means the angle. And you're going to go into a table and you're going to find the height, you're going to find the degrees and minutes, and it will give you a range. They'll have told you a compass bearing, you have to convert that to true to work on the chart, and that will be your start position. Please don't be worried about it. When it comes up in class, don't panic. When we do it together in the app, it'll make perfect sense, hopefully. Next one is horizontal angles. Now, a horizontal angle is very clever. You can do it with a sextant if you wanted it to be exceptionally accurate, or you could do it with a compass. The advantage is that it's a relative bearing, so to say. You take a bearing of that to that. That number will say is 35 degrees. It doesn't matter if you didn't trust your compass. If you didn't know the deviation for your compass, if you didn't know if you've been hit by lightning, or if you're using an iPhone with your compass in it, as long as that bearing is accurate, then your position will be accurate. How does it work? Well, I've written out the notes quite clearly on this because it comes up in the oral exam, so I do want you to be happy with it. If we went to the Bible, so that's the Admiralty Volume of Navigation 1, it says to use a station pointer. So I'll explain what I mean. We'll say that here's our boat and here is the shoreline, yeah? And we've got position A, then we've got position B. B would be better if you could see it, Fred. B, and then we've got C. And these are three conspicuous objects on the chart that you can see. You take a bearing of that, and we'll say that that is 40 degrees. And then you take another bearing between B and C, and we'll say that that is 35 degrees. Happy? So you have taken A to B equals 40 degrees. Then B to C equals 35 degrees. Okay? We don't know where we are. That's what we're trying to work out, isn't it? So I'll just rub those out. We are somewhere on this chart at C, at anchor, and we want to know where we are. We've taken an angle from A to B, and that was 40 degrees. We've used a sextant, or we could have used a compass, a polaris. I don't mind how you did it. And then you've got B to C. If you were going to do this the easy, simple way, you would use a station pointer. What's a station pointer, I hear you ask? Well, this is a station pointer. There's no reason why you can't have one of these in your exam. It says in your exam sheet you can have normal plotting tools. There is nothing abnormal in this. It's a perfectly normal plotting tool. So we'll say we've got A to B. So we said that was 40 degrees. Now this has got 0 there and 40 there, goes all the way around. Okay, so 40, 100, and it goes both ways. So that is basically the center 0. So if we set that to 40, yeah, so that's 0 to 40, based off that line there. And the other one was 35. To 40 and 35, you place it on where all three cut through. You can then put your pencil, and that is where you are. That's it. That's how simple using a station pointer is. You just put the observed angles into the station pointer, and you set them all out. You put it down on the chart. You then put your pencil through the hole, and that is your position. 2 minutes to do that. Sadly, we have to be able to do it mathematically. But once again, that is not actually difficult. I'm going to very quickly show you how to do it. I'm not going to use big words. I'm not going to explain how it works, because you don't need to explain how it works. You need to explain how to do it. So what we do is we draw a line from A to B. Yeah, happy? We then do the hardest part of them all, and that is 90 less the observed angle. So 90 less 40 equals 80, 70, 60, 50 degrees. You then get a you then get a Douglas protractor, if you have one, or just a normal protractor if you don't, and you measure off 50 degrees from A to B. So A to B there, put that down like that, measure off 50 degrees. Yeah, so the bearing, I'll show you what I mean. That bearing there is 50 degrees, which I got from 90 less the observed angle, gave me 50 degrees. I then do the same going the other way, 50. Yeah, happy? I then get a compass. Now that is the same as that, and that is actually the center of a circle. And I draw a circle. I'm not going to stab my whiteboard again. This is not going to be the best ever circle you've ever seen. Circles, if you can draw a perfect circle, it means you've got something very worryingly wrong with you. That A and B should have gone together, to be honest. But you get the idea. That is the center of the circle. You draw a circle, it should pass through A and B and where you are on that circle. I do it later on properly on this chart to show you exactly what I mean. At this point, it's just so that you understand the concept. You then repeat exactly the same for B to C. So you draw a line from B to C. You do 90 less 35, so that must be 55. You then measure off 55 degrees, that baseline. Yeah. That is now the center of another circle, and you draw another circle. Run out of. And where it crosses is your positional fix. That's it. So you draw a line from A to B. 90 less the observed angle gives you a number. You measure off that number from that line from A to B. Yeah. You then do the same for the other side. Where they cross in the center is the center of a circle. You draw a circle, it should pass through A and B, if you're better at drawing. And then you repeat for the second one, and it will give you two possible positions. One will be on the land, and one will be at sea. You can discard the one that's on land, hopefully. If you're on land, probably not the biggest of the problems trying to work out where you are. Happy with that? As I said, we'll work through a full example of how it could be presented in an exam and do it together on, I think it's chart 5048 inside the device. I've given full explanations on that inside, and then we've got danger angles and fix the ship's position using the echo sounder. So let's have a quick discussion of the danger angle. A danger angle is when you decide how far you want to be off, and you say that we must be more than 1 mile. You find the height of the object, you go into Norris, and it says that the angle must be more than 40 degrees, yeah, or 0 degrees, 40 minutes. You set up on the sextant, you look at the object. If the object is below the land, it means you're on the safe side. If not, you're too close. Practical use of it, you're required to pass 5 cables clear of the rock shown above. This is 8 cables from a lighthouse, 29 meters above mean high water. You could work out the predicted height of tide to make it more accurate. Set the angle on the sextant. Provided the reflected image of the lantern appears below the sea level, the ship is outside the danger. It's like saying we shouldn't be any closer than 20 degrees. If we are closer than 20 degrees, we are inside the danger zone. So it's a very quick way of working if you're inside or outside of your preset danger. Yeah, happy? Very simple. I've done one example of how it could be used to help you find a course to steer to a certain waypoint, the danger angle of X amount, or you must pass. It effectively is you must pass more than 3 miles from this point. Fix the ship's position using an echo sounder. Okay. We've got a bit of land there, and we've got a point there, A. And what you can do is you've got a position line from it, and then you could use your depth adjusted for height of tide, adjusted to the water line, or adjusted to depth below keel. And as you pass over these contour lines, if that was, we'll say, the 10 meter, 20 meter, 30 meter, you could ascertain where you are. If you knew you were accurately on the 10 meter contour line, you could say that that is where you are at 12 o'clock. Yeah, so you take a bearing using a compass, and that will give you a position line, and then you use the depth as a means of finding your range from that object. Last one, a beam. A beam is 90 degrees to ship's head. What I want you to do is put your arm out, point forwards. A beam is 90 degrees to ship's head. So put your arm out the port side or your arm out the starboard side. That is 90 degrees. You must work it from ship's head. Not your water track, but what the question says is your ship's heading. Okay? I hope that's helped you, and I hope the EP work through question has helped. Hey guys, a very quick one. I am currently working on part B, and I would like to make a win-win for you and for me. If you send me an email at fred@fredsoralprep.com and tell me when you are sitting your nav and radar exam, I will send you some of the theory questions, the part B questions that I have been working with. And in return, after your exam, I would love for you to tell me what questions came up or what style of question came up for part B. So send me an email, fred@fredsoralprep.com. Tell me when you're sitting your exam, and I will give you some suggestions on the style of recent exam questions. I'm not going to give you the questions that are coming or exact past paper questions, but what I will do is help you develop a probability or some of the most recent or likely exam style questions. Send me an email. I will ask you to prove that you bought this app. So please send me a screenshot, the receipt from Apple, to prove that you downloaded the app or you bought the app. Okay? Help me help you. Good luck with the exam. Hope you can do the chart work now. Good luck.